This is part 3 in our video tutorial on the gas laws. So in this video clip we'll be looking at Dalton's law of partial pressure, as well as the Avogadro's law, and finally the ideal gas law. So let's take a look at Dalton's law of partial pressure. Now Dalton's law of partial pressure is pretty self-explanatory. It's not so much an equation as a concept. So what Dalton's law of partial pressure states is that if I have a gas or a mixture of gases here, like in this case I've got a balloon full of oxygen, nitrogen, hydrogen gas, well, the total pressure inside the balloon is equal to the pressure of the first gas plus the pressure of the second gas plus the pressure exerted by the third gas, and so on and so forth. So if there are more gases, then you'd have to add them all up. So that's pretty self-explanatory, nothing too fancy there. Now the second part to Dalton's law of partial pressure may not be as obvious, but it does make sense. What it states is if nitrogen makes up 50% of the gas's volume, or the balloon's volume, then it should be 50% of the total pressure. So for instance over here, if my total pressure of my balloon is 100 kilopascals and nitrogen makes up 50% by volume, then it should be 50% of the total pressure. So 50% of 100 is 50 kilopascals. Same thing over here. Since oxygen makes up 35% of the balloon's total volume, then it should be 35 kilopascals out of 100 kilopascals. And the same thing goes with the hydrogen gas. 15% of the total volume, therefore 15% of the total pressure, which is 15 kilopascals. So let's try a sample question. So first I'll start off with my givens. What am I given? I'm given that a 5-liter balloon contains 3 gases. So at this point I know that the total volume of my balloon is 5 liters. V total equals 5 liters. It contains 3 gases, nitrogen, oxygen, and hydrogen. Now the total pressure inside the balloon is 175 kilopascals. So P total is equal to 175 kilopascals. Now it says the partial pressure of oxygen is 45 kilopascals. So the pressure of just the oxygen is 45 kilopascals. So the question is now asking me, required, what volume of oxygen is present in my balloon? VO2 equals what? Now with partial pressure questions, I generally like to draw a diagram of the whole situation to get a layout of what the problem is asking me. So here I've drawn 2 balloons, one describing the situation in terms of volume, and the second balloon describing the situation in terms of pressure, kilopascals. As you can see, in this case over here, I know the total volume of my balloon is 5.0 liters, and the total pressure of my balloon is 175 kilopascals. However, I also know that the pressure of just the oxygen is 45 kilopascals. Now if we look back here, we see that Dalton's law of partial pressure relates pressure and volume together. If the volume of the nitrogen gas is 50% of the total volume, then it should be 50% of the total pressure. So going back to my problem, what I need to do is find out what is the percentage of this partial pressure of oxygen out of the total. And then once I find the percentage over here, I can find the percentage of the volume over here. So to find the percent of the oxygen, I take the 45 kilopascals, divided by the total pressure of 175 kilopascals, then multiply by 100%, and you get 25.7%, which means that this should be 27.5% of the total volume of 5 liters. So if I want to know what volume that's going to be, then I need to do 27.5% of the 5. So I have the 5 liter total times 27.5% out of 100%, which gives me 1.375 liters. So the volume of the oxygen over here, 1.375 liters. This out of the 5 liters represents 27.5% of the total volume. So notice how we can relate volume and pressure together in these two situations. So like I said, with Dalton's law of partial pressure, there is no real equation per se. It's more of a concept, an idea of how to relate these two. Mostly it's just ratios, setting up your ratios between them. Now the next law we'll be looking at is called Avogadro's law, and it states that at constant temperature and pressure, so the temperature and pressure must remain the same, then equal volumes of all ideal gases contain the same number of molecules. Meaning, if I have 3 liters of oxygen gas and the temperature and pressure don't change, then 3 liters of nitrogen gas would contain this exact same number of molecules as this one over here. Similarly, if I have 3 moles of oxygen gas and 3 moles of nitrogen gas, then they should have the same volume as each other as well. Thus the equation mole of gas number 1 divided by the volume of gas number 1 should be the same as mole of number 2 and volume of gas number 2. Now these ratios are interchangeable, so I can also flip it the other way around. Either case is acceptable. As you can see, 1 over 2 is equal to 3 over 6. But if I flipped it, so it's 2 over 1, and I flipped it, so it's 6 over 3, this is also equal as well. So that's why flipping these two, find the inverse, it doesn't make a difference. Alright, so this is Avogadro's law. This only works at constant temperature, constant pressure. Mole of the first gas over volume of the first gas is equal to mole of the second gas over the volume of the second gas. Now the next thing we need to discuss is called standard temperature and pressure, also known as STP. So if you see this acronym STP, it basically means that the situation is under standard temperature, which is 0 degrees Celsius or 273.15 kelvins. They are equivalent to each other, as well as standard pressure, which is 101.325 kilopascals. So remember, as soon as you see the word STP or the acronym STP, you know what the temperature is and what the pressure is. These are numbers you're going to have to memorize. Now, also in that STP, you'll find that the molar volume of an ideal gas is 22.4 liters per mole. So molar volume is measured in liters per mole. So how many liters of gas per mole of that gas is present? So if you have 1 mole of any ideal gas at STP, so under these temperature and pressure situations, it'll automatically have a volume of 22.4 liters. Alright, so let's try this next sample problem. A balloon is filled with oxygen gas at STP. So as soon as I see the acronym STP, I know that the temperature is 273.15 kelvins and the pressure is 101.325 kilopascals. Alright, so you're just going to have to memorize these numbers, unfortunately. So anytime you see STP, you have to write down the numbers 273.15 and 101.325. Now the final volume of the balloon is 7.5 liters. V is equal to 7.5 liters. Now in this case, we don't see any other temperature or pressure or volumes. So I don't have to write the P1, V1, and T1 because there is no T2 or P2 or V2. Alright, so what am I trying to find? I'm trying to find how many mole of oxygen is present. So mole of oxygen. So at this point, I look at my approach. Since this situation occurs at STP, I know the other magic number is 22.4 liters of gas for every 1 mole of any ideal gas. So oxygen over here is the ideal gas. I want to know how many moles there are, so I have no clue how many moles there are. But I do know that the volume is 7.5 liters. Now, like I said before, if your algebra is kind of wonky, I recommend that you flip your unknown so it's always at the top in the numerator. So it becomes x over 7.5 liters. So I just switched it. X number of moles, 7.5 liters. But if I flip it on this side, I have to flip it on this side. So it becomes 1 mole for every 22.4 liters. So at this point, now I can just cross multiply out there, and I get 1 mole times the 7.5 liters divided by 22.4 liters per mole, and my final answer is 0.335 mole of oxygen gas. Alright, so we were able to use Avogadro's law where the mole and volume ratios are identical as long as the temperature and pressure remain the same. And since the temperature in our question does not change, we are allowed to use Avogadro's law. And so I know that at STP, the temperature is always going to be 273.15 kelvins, or 0 degrees Celsius, 101.325 kilopascals. And the molar volume of any gas, doesn't matter what type of gas it is, as long as it's ideal, is going to be 22.4 liters for every mole. So I use that as my original ratio. 22.4 liters for every mole is equal to 7.5 liters per mole. Then I flipped it so I get make my algebra a little easier and solve for the unknown, which happens to be 0.335 moles. Our final topic deals with the ideal gas law, which is a combination of the combined gas law and Avogadro's law. So when we combine these two equations together, we get PV is equal to nRT, where pressure and volume have an indirect relationship. That's why it's PV at the top. And if I wanted to rearrange this equation, T would be at the bottom over here if I took it out from this side. And that's where the T comes into play. Now, I'm going to reverse that over there. So P stands for pressure. Pressure must be measured in kilopascals for this equation. You must always convert to kilopascals. Volume must always be converted to liters. That's one of the major errors a lot of students will make. The question might give it to you milliliters. You must convert it straight up into liters. T is the temperature, and that's always measured in kelvins, so make sure you don't have degrees Celsius in there. N represents the number of moles, so that's where we get Avogadro's law, and we place it in here. However, R is the new one. R is known as the universal gas constant, and it is 8.314 kilopascal liters per mole Kelvin. So again, you're going to memorize this number as well. So there's a lot of numbers to memorize in this particular unit. Now, where did this number come from? This is an experimentally derived number. So through multiple experiments, they found that 8.314, when you plug it in here, it allows the whole equation to work out nicely. Now, if you ever forget this number, what you can do is solve the ideal gas law at STP. So if I rearrange the equation, PV is nRT, and I want N to be on this side, so I go PV divided by N and divide by T, so the T's cancel out, the N's cancel out, but if you do it on this side, you're going to have to do it on this side as well. So it becomes PV over NT is equal to R at STP, and start plugging in the numbers. Now, because I know with STP, the standard pressure is 101.325 kilopascals, and standard temperature is 273.15 kelvins, and I know that at STP, 1 mole of any ideal gas will have a volume of 22.4 liters. And if you plug all these numbers in, you get 8.314, and take a look at that, kilopascal liters per mole Kelvin. And that's where we get the universal gas constant from. So if you forget this number, you can always just plug in your values for STP and you can calculate it out there. Now, how I like to remember this is I think of 8 pi. So for instance, 8 sounds like 8. Then I 8 pi. Well, pi is 3.14. So if I say 8 pi kapal molk, I don't know, whatever way works for you, however you want to memorize it, as long as you keep that in mind. Alright, so unfortunately it looks like I'm running out of time on this video clip as well, so I'm going to have to continue this on the next video clip. I'm pretty sure that one is going to be the last one though. Alright, so I'll see you in the next clip.